Welcome to the deep dive. Today, we're plunging into a type of motion you genuinely see, well, everywhere.
Absolutely. Think about things moving back and forth, repeating themselves.
Right, that repeating pattern. But we're drilling down a bit today.
We're moving past just any repeating motion, like, say, a planet going around the sun. That's periodic, sure.
But it's not quite the back and forth we're focused on. We're looking at oscillatory motion.
Exactly. The to and fro movement around a central kind of stable point. Think of a kid's cradle or, a swing.
That equilibrium position is key, isn't it? The spot it always wants to return to.
It is. It gets pulled away, then pulled back over and over.
Okay, so within that oscillatory world, there's this really fundamental type. It pops up constantly in physics, especially when you're looking near stable points.
That's Simple Harmonic Motion, SHM. If you're getting into physics, particularly A-level physics, this is, well, it's core. You can't avoid it.
And it's described as the simplest kind of oscillation.
Pretty much. It's elegant. What makes it SHM, what really defines it, is a very precise link between acceleration and position.
Okay.
The acceleration of the object. It's always pointing back towards that equilibrium spot. Always.
Pulling it home.
Yes. And this is the crucial part. The strength of that acceleration, its magnitude, is directly proportional to how far the object is from that center point.
Ah, so the further you stretch it, the harder it snaps back. That snap being the acceleration.
Exactly that. And it's a linear relationship. Double the distance from the center, you double the acceleration pulling it back. That proportionality is the absolute signature of SHM.
So, important point, SHM is oscillatory.
But not all oscillatory motion is perfect SHM. Real-world stuff has friction, maybe the force isn't perfectly linear, but SHM is our ideal starting point, our clean model.
Right, the theoretical baseline. So the two big takeaways for SHM characteristics are, one, it's periodic, it repeats.
Definitely periodic. And two, that defining feature we just nailed, acceleration is proportional to the displacement from the mean position, and crucially, it's always directed back towards it. That gives you the restoring force.
Okay, let's see this in action. Where does this rule acceleration, proportional to displacement, pointing back, actually show up? First example, the simple pendulum.
The classic, but with a condition, remember.
Right, it's only really SHM for small swings, isn't it?
Exactly. Less than about 10 degrees from the vertical, give or take. Picture it. A mass, the bob, on a light string, fixed at the top. Pull it sideways just a little, let go.
Okay, I see it. Gravity pulls down, tension pulls up along the string. But the force making it swing back is a component of gravity, right?
Yeah.
Along the arc.
Precisely. That component works out to be menzimuth. The minus sign tells you it's a restoring force, pulling back to the lowest point.
And here's the small angle trick.
Yes. For small angles, sin is almost identical to A itself, if S is in radians. It's a fantastic approximation.
And the actual distance along the twin path, let's call it x, is linked to the angle in string length, L. So x equals all, which means L's about x.
Perfect. Substitute that into the force. F is roughly mg times x.
Okay, then Newton's second law, ESMA. So mg/mg/SL.
Yep. And just rearrange that. The mass m cancels out.
And you get a SGLX. There it is. Acceleration equals a constant GL times displacement x. It fits the SHM definition perfectly.
It does. And straight from that, we see the term multiplying x, which is always SK, the square of the angular frequency. So here, S must be GL.
And O tells us how fast it oscillates. The period, T, the time for one full back and forth, is always 2 divided by O.
So T OX 2 could T, a beautiful result.
And it only depends on the length of the string and gravity, not the mass, not how wide the swing is, as long as it's small. Amazing.
It really is. Goes way back to Galileo noticing this. Of course, in reality, air resistance slows things down. The amplitude shrinks.
Damping, yeah. But this formula is the ideal SHM. Yeah. Okay, next classic, the mass on a spring. This one feels maybe more direct with the spring force.
I think so, too. Imagine a block attached to a spring sliding on a frictionless table. Equilibrium is just the spring relaxed.
Pull it or push it, the spring fights back. That's Hooke's law.
Hooke's law, exactly. For an ideal spring, FD equals Kx. Force is proportional to displacement x, opposite direction. K is the spring constant stiffness.
Okay, F again, so it goes KF mod.
Right, and look what happens when you rearrange. A back pay x.
Bingo. Same form again, acceleration proportional to displacement, negative sign means it's restoring. So if here is kilometer.
Precisely.
And the period, T, with 2 parts, is this T equals 2.
Makes sense, right. More mass, m, means it oscillates slower, takes longer, so T is bigger. Stiffer spring, bigger K, means it snaps back faster, T is smaller.
Yeah, that feels intuitive. What about hanging the spring vertically? Gravity gets involved then.
It does, but it's neat how it works out. Gravity pulls the mass down, stretching the spring to a new equilibrium position. But if you then measure displacement from that new spot, the analysis for SHM still holds, and the period formula is exactly the same. T is exactly the same. T equals 2mk. Gravity just shifts the center point.
Oh, that's clever. The underlying oscillation physics is the same.
It is, and you can do things like connect springs together in series or parallel and figure out the effective spring constant for the system. It all follows from these principles.
It's really powerful how the Sanitax relationship keeps showing up. Let's hit that third example. Liquid in a U-tube. This one's less common, maybe?
Maybe less intuitive at first glance, yeah. But it's a great example of pressure acting as the restoring force. Imagine a U-shaped tube with some liquid in it. Levels equal is equilibrium.
Okay. Push one side down.
The other side goes up by the same amount. Let's say you push down by x, the other side goes up by x.
So the total height difference between the two surfaces is 2x.
Exactly. And that height difference creates a pressure difference at the bottom of the U, proportional to 2x times the density or times g. This pressure difference, acting over the tube's area A, creates the restoring force. F equals 2xg.
Got it. And the mass that's actually oscillating, it's the whole liquid column. If its total length is, say, 2h.
Then the mass m is density times volume, so m2ha.
Could put it together. Fma gives messity 2x edge AA,
And look, the R and A cancel out.
leaving AHHX. Unbelievable. It's the same form again.
It really is. SHM pops up again. Here, oak is D.
And the period T is 2A, is TUA equals 2A. Depends on gravity and half the total liquid length.
So gravity on a pendulum bob, spring stretch, liquid pressure difference. If the setup leads to that proportional restoring force, you get SHM.
It's a unifying idea. And there's that connection to circular motion, too, which helps visualize it.
Oh, hugely helpful. Think of something going around in a circle at a steady speed. Now imagine projecting its position onto one line, like a diameter of that circle. Just watch the projection, the shadow.
It goes back and forth, speeds up in the middle, slows down at the end.
It's exactly like SHM. It is SHM. This isn't just a visual trick. The maths lines up perfectly.
How so?
Well, we know how to describe uniform circular motion. If the circle's radius is A, that becomes the amplitude of the SHM, the angular speed is O. The projection's position, say on the y-axis, is given by y is A sin h, or maybe A cos t, depending on where it starts.
Standard trig for circular motion.
And if you know the position equation, you can find the velocity and acceleration equations using calculus or just the relationships from circular motion.
You find the velocity v at displacement y is v is butt fess, ayy, max speed at the center, zero speed at the ends, YRAA.
Checks out. And the acceleration.
Comes out as a y, which is just our definition of SHM again.
Yeah.
Derived from a completely different angle, the circular motion projection.
It's a fantastic cross-check and gives us all the equations we need to describe the motion. Fully position, velocity, acceleration, all as functions of time or position.
And this ties into phase.
Yes. That term inside the sine or cosine, like plus in y will s in plus s, that's the phase angle. It tells you exactly where the oscillator is in its cycle at any given time t.
Like a progress tracker for the oscillation.
Kind of, yeah. It wraps up both position and direction, and that fitbit, the initial phase, is just the phase angle when you start the clock at t0. It sets the starting conditions.
Okay, makes sense. It pins down the starting point. Lastly, energy in SHM. We said it's ideal, no friction.
So energy should be conserved, and it is. It just swaps forms.
Back to the spring. You've got kinetic energy, 12 milliVA, energy of motion.
And potential energy stored in the spring, 12 kFracs.
The total energy E is just the sum. E equals 12 milliVA plus 12 kRH, and this total value stays constant.
That's the key. It never changes in ideal SHM.
And at the very ends of the motion, at x plus a or equals an a, the velocity is 0 for an instant.
Right, so all the energy is potential at that moment, which means the total energy E must also equal 12 carry ASAO. It's locked in by the amplitude and spring constant.
So energy sloshes back and forth. All potential at the ends, all kinetic as it zips through the middle, and a mix in between. But the total amount is fixed.
Exactly. Proportional to the square of the amplitude.
Okay, so let's wrap this deep dive. Simple harmonic motion, SHM, it's this specific foundational kind of oscillation.
Defined by that crucial rule. Acceleration is proportional to displacement from equilibrium and always points back towards it. ACA, SAX, that's the heart of it.
We saw it in pendulums, small swings. mass spring systems, even liquid in a U-tube. Derive the period for each.
Linked it to the projection of circular motion, which gave us the equations for displacement, velocity, acceleration, talked phase.
And cover the energy conservation, swapping between kinetic and potential, with the total fixed and related to amplitude squared.
And understanding this matters because SHM is the basic building block. It's the simplest model for vibrations for anything oscillating around a stable point when the movements are small.
So for anyone studying physics, getting SHM isn't just about these specific examples.
No, it's about understanding a fundamental behavior of nature. It opens the door to waves, sound, light, circuits, quantum mechanics. Small oscillations are everywhere.
It really is foundational. So the final thought for you listening, now you know the signature of SHM, that a Nesek-Sophex rule. Where else might you see it, beyond the textbook examples?
Yeah, look around. Things vibrating, humming, swaying gently. Could some of that be approximated as SHM? Maybe parts of musical instruments, structures, even biological systems? Keep an eye out for that pull back towards equilibrium. SHM might be closer than you think.